所以呢，你就相当于从 Testing, testing. Okay, good evening. So we will continue the discussions. Just to recap a little bit. Last week we were talking about the first the one-star trouble, right? The one-star trouble introduced by the frequency flat fading was that the error probability curve was decreasing as we increase the signal-to-noise ratio, but decreasing slowly, right? The first-order penalty is characterized by the slope, right? The slope is being very small. So therefore, the solution roadmap is to exploit diversity. So last time we explained what is diversity, right? Remember, diversity is we try to make use of multiple independent observations before making a decision. That's called diversity. And then we go on and explain where can we create diversity observations, right? We explain it can be coming from time, can be coming from frequency, right? And then, but both time and frequency diversity requires there will be penalty on the spectral on the spectral efficiency, right? So and then we go and talk about a third dimension of creating diversity is received spatial diversity, and then with received spatial diversity, so basically the transmitter just transmit the same information, the same symbol, once. Just make use of channel one time to send one symbol, right? And then the receiver, having multiple receive antennas, will be able to pick up multiple observations about the transmission. And these multiple observations will suffer from independent fadings if the separation of the two antennas are sufficiently large, right? And then we talk about how large is sufficiently large. And the advantage of received spatial diversity is you have full diversity. So if you're talking about two receive antennas, you can have a diversity order of 2, okay? And also what we call full rate, meaning that you have 100% throughput, 100% spectral efficiency. Okay, so you don't have any penalty on the spectral efficiency. And then what's more is here there is one additional feature. This is the received spatial diversity is entirely a receiver technology. It is totally transparent to the transmitter. So it's transparent to the transmitter. And therefore, this is standard independent. So that means this technology can be used to improve the performance of Wi-Fi, 3G, 4G, LTE, whatever. Okay, you don't need to change the standard to implement this solution. So that would be the key features of received spatial diversity, right? And then, but the only problem is this spatial separation needs to be larger than the coherence distance, right? And then this coherence distance at the mobile station is still pretty, is half lambda usually, okay? So the problem is the receiver handset usually have very limited real estate, so you cannot put up too many independent antennas. So therefore, people start to think about another topology. What about transmit spatial diversity? With transmit spatial diversity, the idea is to try to install multiple antennas on the transmitter side. Because people believe that at the transmitter, let's say the base station as a transmitter, is much bigger. You have more space to install more independent antennas, right? So, and that's why people start to consider installing multiple antennas at the transmitter, and then and see, can we have the same benefit as the received spatial diversity? That is, can we achieve full diversity order and also full rate with this second topology? People would expect this is pretty symmetrical initially, and they wouldn't expect they would expect you should be able to achieve whatever can be achieved in the received spatial diversity. But turns out that this received spatial diversity was invented around 60s. But turns out that it took people decades of effort in order to find out a solution for transmit spatial diversity that can achieve full diversity order and full rate as received spatial diversity. So it was a solution was only found in late 90s. Okay, so that's that case from the received spatial diversity. So it turns out that it's not obvious, and it's not symmetrical. Okay, for example, received spatial diversity, you can achieve these benefits for any number of received antennas. But later on, as we explained, for the transmit spatial diversity, you cannot have this kind of full benefits for any number of transmit antennas. It only works for a certain number of transmit antennas. And that investigation spin off the whole field of what we call space-time coding at the end. Okay, so let me explain that before we have the solution. The best way people can utilize this tool with transmit antenna was like this. So let's say this is the time, and then this is the antenna number. This is first antenna, second transmit antenna. So no matter how they do it, they find that in order to use to create two diversity observations, you have to use the channel 2 times. Okay, so in the first transmission, in the first symbol, so you just transmit a modulation symbol S on the first transmit antenna, and transmit nothing on the second antenna. So in this way, you created one observation, right? So this observation will be coming from received by the received antenna in the first time slot due to this transmission. Okay, alpha 1 is the fading coefficient from the first transmit antenna to the receive antenna. Is that okay? And then in the second time slot, so what they do is you transmit nothing on the first antenna, and you transmit the same modulation symbol on the second transmit antenna. So in this way, you generate a second observation. Y2 equals to alpha 2 S plus N2. Is that okay? So alpha 2 is the fading coefficient between the second transmit antenna to the receive antenna. So in this way, you created two observations over this two times slot, right? And then these two observations contains the same information, but then they suffer from different fading, right? So similarly, in order to be called diversity observation, the spatial separation of the transmit antenna needs to be larger than the coherence distance in this case. Okay? And if this is the base station, the coherence distance will be much larger. It's around, if this is the base station, it's around 10 lambda for, let's say, New York City, this kind of propagation environment. All right, so in this way, you created two diversity observation. Okay? But this is not quite the same performance as received spatial diversity, right? Because now, yes, you have a full diversity order. Is equal to 2. But what about the spectral efficiency? Do you have 100% spectral efficiency? No, right? Because you have to use the channel 2 times, right? To deliver one symbol. So in this case, you only got 50% of the spectral efficiency. This is not the same as received spatial diversity, where you have 100% of the spectral efficiency, right? So that's not the best way to utilize the transmit antennas. But that's around early 90s. That's the best way people can use two transmit antennas. Okay? And this scheme is called time switch transmit diversity, something like this. And it was once proposed in the standard when we were trying to standardize the 3G, one of the 3G system. Okay, so seems there is no solution, but around late 90s, let me erase this. Around late 90s, there was a guy called Alamotti. So he invented, so he finally found a way to do it, okay? Achieving, with this two transmit antenna topology, achieving full diversity order and 100% spectral efficiency. The way they do it is like this. So this is time, this is antenna. You still need to use the time slot, you still need to engage in two transmissions. Okay, but the way they do it is like this. In the first time slot, so you transmit S1 and S2 on the two antennas simultaneously. S1 and S2 are two independent modulation symbols. Okay, so this transmission will induce an observation, right? So in this case, this observation is given by alpha 1 times S1 plus alpha 2 times S2 plus noise. Is that okay? Now in the second time slot, you transmit the following: minus S2 conjugate, S1 conjugate. Now conjugate is a compressed conjugate. So this is, so assuming we are talking about, let's say, MQAM family. So the signal space is two-dimensional, right? So you have ith axis and the qth axis. So each of these constellation points would be a two-dimensional vector, right? So each of these constellation points would be living in R2, right? But for any R2 vector, we can also represent this as a C1 point, compressed. Okay, so any two-dimensional vector can be mapped to a one-dimensional compressed number, right? The real part would be the x coordinate, imaginary part would be the y coordinate. Is that okay? So so each of these points is now represented as a compressed number. So compressed conjugate is in the usual sense. So you treat each of these S1, S2, these modulation symbols as a compressed number, which encode the x coordinate and the y coordinate in their real part and imaginary part. So this conjugate means if S1 is A plus BI, compressed conjugate becomes A minus BI in the same way as how compressed number operates. Okay? So in the second time slot, they transmit S2 minus S2 conjugate, S1 conjugate. So in this way, you generate a second observation. The second observation is given by alpha 1, the fading coefficient between the first transmit antenna and the receive antenna, multiplied by whatever you transmit here. So it's minus S2 conjugate, plus alpha 2, multiplied with whatever you transmit here, S1 conjugate. Okay? Let me further erase this. Plus the noise. So in this way, you generated two observations. Now, the thing is, to the receiver, you receive Y1 and Y2, right? Over this two time slot transmission. So what is your goal? The receiver is to try to, based on this observation, trying to decode for what? Decode for S1 and S2, right? S1 and S2 will be your unknown, the data being transmitted. So you can think of each observation as one equation. So this first observation is an equation, is a linear equation in S1 and S2, the two unknowns, right? The second equation is also the second observation gives you a second equation about the unknown S1 and S2, right? But the right-hand side is not exactly in terms of S1 and S2, it's in terms of S1 conjugate and S2 conjugate. So let's do some operation to make it clear. So we can apply conjugate on both sides. If we apply conjugate on both sides, so the second observation becomes Y2 conjugate equals to minus alpha 1 conjugate S2 plus alpha 2 conjugate S1 plus N2 conjugate. Is that okay? Just applying conjugate on both sides. So in this case, the conjugated observation would be giving you a second equation in terms of S1 and S2 as well. Okay? So in this way, you have two equations, two unknowns. The two unknowns are S1 and S2. The two observations give you two equations, right? In terms of S1 and S2 would be your unknown. So these are linear equations. And you can write this in a matrix form, right? Try to write this in matrix form. You will have Y1, Y2 conjugate equals to a coefficient matrix times S1, S2, right? Plus the noise. So this coefficient matrix would be, if you read, this is alpha 1, alpha 2. So alpha 1, alpha 2 here. And this is alpha 2 conjugate minus alpha 1 conjugate. Is that okay? So then the problem, the detection problem at the receiver would be very simple. This is the observation vector you have after some post-processing on the second observation, right? So this is Y1 and Y2 conjugate as something you know. And then S1, S2 are the unknown. So you can actually solve this, solve for S1, S2 based on this, right? So the solution would be S1 hat S2 hat will be simply given by this coefficient matrix inverse times y1, y2 conjugate. Okay? So this is how the receiver obtain the data, transmitted data from the observation. Now, of course, there are further analysis, but I try to skip the math, detailed math, as I think you will be able to. I think in some other courses you will have a more detailed mathematical deliberation. But what I wanted to say is, if you try to solve for this equation like this, you will find that, that you can see that this equation will have full diversity, because each of this coefficient would be in terms of the magnitude of alpha 1 square plus magnitude of alpha 2 square. So this will basically give you the diversity order of 2. And moreover, if you look at the rate here, do you have any penalty on the spectral efficiency? Now you use the channel 2 times, right? But now how many symbols can you deliver? 2 independent symbols. So 2 symbols over 2 times log. So you still have full rate, 100% spectral efficiency. Can you see that? So you have 100% spectral efficiency and you achieve full diversity order. This is exactly what you get from received spatial diversity, right? So finally, people figure out how you can actually make use of this transmit multiple antenna on the transmitter side to achieve the same performance as received spatial diversity, okay? And why it took people decades of effort to find out the solution? Conjugate is a nonlinear operation. So this arrangement is actually a nonlinear processing. So over decades of effort, people have been just focusing on linear processing only, because that's most of kind of a straightforward way to consider processing. So it turns out that this solution requires some nonlinear operation. Okay. So and this scheme is called Anamurti coding. And this performance, the same performance as received spatial diversity, only works for a few number of transmit antenna. It only works for 2 transmit antenna and 4 transmit antenna. Okay, so for some other number of transmit antenna, it wouldn't work this way. Okay, so it turns out that these 2 topology are not the same. They are not symmetrical. Is that okay? And this is called space-time coding. So after this attempt, so people basically for, I guess, almost the 10 following years, people have been, very excited about this, designing some other way of transmitting symbols so as to achieve full diversity and full rate. Okay, so that field is called space-time coding. So now when I talk about, so received spatial diversity is one other advantage, as I just mentioned, is standard independent, because it's transparent to the transmitter, right? And last time I explained the goal of standardization is to achieve interoperability, right? So that different transmitter and receiver from different companies, as long as they conform to the same standard, they can talk to each other, right? This is called interoperability. However, we don't want to over-standardize things, right? So therefore, the compromise is to achieve this goal of interoperability, the standardization process usually will tightly specify the transmitter, but loosely specify the receiver, so that different companies will still have some rooms for innovation so that they can compete by performance. Okay, so that was the situation. So now, if your invention is on a received spatial diversity, so the solution would not involve any standard, because the receiver design is outside the scope of standards most of the time. So, and therefore, if you work for a small to medium-sized company, they welcome that kind of solution, because you don't need to play the standardization game, and you can still utilize the solution to improve your product's performance. But if you work for big companies, big vendors, so they do not welcome that kind of solution, because there won't be any chance of creating what we call standard essential pattern, right? So you patent this idea, but this idea cannot be adopted into the standard. So the value of this patent would be usually not that valuable, because the burden of proof of infringement would be very high. Okay? But for transmit spatial diversity, it's a different story. Now, if you work for a small company, now first of all, if you are the one who invented this this particular scheme, do you need to change the standard to adopt your solution? Of course, right? Because this is a special way of transmitting the symbol in such a special arrangement. If the standard originally do not have that kind of provisioning, in order for the system to benefit from this scheme, you need to change the standard. You need the standard to adopt your solution so that the transmitter symbols from the transmitter will have this kind of arrangement, right, in order to create so-called diversity observations, right? So it involves the transmitter, and therefore you need you need your solution to be adopted into the standard, right, before it can be realized. So if you work for small to medium-sized company, this is a bad news, because that means it's a huge overhead and huge cost associated with adopting this solution. But if you work for big companies, this is exactly what they are looking for. If you work for big companies, they will first file a patent for this scheme, and they will try their best to push this arrangement into the standard. Okay, and that's exactly what happened. So this patent has been this solution has been patented and has been adopted in any modern wireless standard, as however you can think of. For example, it is adopted in Wi-Fi, it is adopted in 3G, 4G, 5G. Okay, so it becomes very valuable. But of course, right now we don't need to worry about that, because that patent has expired. Okay, it was in mid-90s, and then so by now it has expired already. But this is one example of a very valuable standard essential patent. Okay. All right, so this is the different ways of creating diversity observations. All right, you have transmit spatial diversity, receive spatial diversity involving multiple antennas. And you can mix these two together, obviously. You can have multiple antennas on the transmitter and receiver as well. So in this way, for example, if you have 2 transmit antennas and 2 receive antennas, the full diversity order would be 4, okay? Would be 4. Because you think about all the possible alpha, you have 4 independent alpha, right? So maximum diversity order would be 4. So, and for a very long time, people basically expect these multiple antennas, the key benefits of multiple antenna systems, either at the transmitter side and or at the receiver side, would be diversity. You try to create diversity observations without any penalty on the spectral efficiency. That's the goal of the benefit people expect from multi-antenna system. But at the similar time of multi-code, which is in the late 90s, so there is another way to utilize this multi-antenna system, and now it is called MIMO, multi-input, multi-output, and that was invented from Bell Labs, in fact, in mid-90s. So at that time, people figured out if you have multiple transmit antenna and multiple receive antennas, there are more than there are something extra you can benefit from in addition to diversity, and that was called spatial multiplexing. So we will talk about that part later on. Okay, so for now, just back to the roadmap, we are talking about diversity. So having multiple antennas at the transmitter and or the receiver would be another way to create diversity observations. Is that okay? So far, we answered the first question, how can we create diversity observations? Okay, the solution was it can be created from time, it can be created from frequency, it can be created from space. Okay, so that was the 3 major techniques to create diversity observations. Okay, now with this, let's look into the second question. So suppose we have created diversity observations. How can we make use of that before making a decision? So let's say now this is the receiver. And somehow, let's say we have created multiple independent observations. For example, we have the first observation given by alpha 1s plus noise. second observation given by alpha 2s plus noise. And then in general, we have L observations. Okay, so these are the diversity observations. Available at the input of the receiver. Okay, now the question is how to make use of this before we make a decision. Okay, so previously when we talk about digital modulation, we say that the demodulator should do something called minimum distance demodulation, right? The minimum distance demodulation, once again, if you look at the input is one observation, the output will be the detector symbol, and here you apply minimum distance, right? So with this minimum distance demodulation, how do you interface with multiple observations at the input? So the proposed architecture will be something like this. We have to do something called diversity combining. So we have to think of some way to combine this multiple observation into some metric. I call this R. And based on this combined metric, we pass on to the demodulator, the minimum distance demodulation, and then we do the detection based on that. So the receiver, the overall receiver will be like this. Okay, and now the second question concerns about how do we do diversity combining? How do we combine these multiple observations to harvest the benefit of diversity? Okay, what is the benefit of diversity? The error probability curve, the slope of the error probability curve will be steepened, okay, by the diversity order. So that's the benefit. Okay, now I'm going to explain 3 common ways of so-called diversity combining. The first way is very straightforward. The first way is called selection combining. So what do we mean? Now if you take a look at this observation, each of these observations consists of 2 terms, right? So if we take a look at this observation, there are 2 terms. This term is a good term. Good term means this term contains something that is related to the symbol I'm interested, right? I'm interested to do detection on the transmitter symbol. So this term is related to the symbol that I want to detect. So this is a good term, right? This term is a bad term because it's a noise. The noise has nothing to do with the transmitter symbol, right? So therefore, the reliability of an observation depends on what? Depends on the ratio between the good term and the bad term. If this observation has very large alpha, magnitude of alpha, by the way, this alpha is the fading coefficient, it's a complex number. So this fading coefficient have 2 effects. The magnitude of alpha gives you attenuation. The argument of this alpha gives you phase rotation, okay? So if the magnitude of this alpha, the so-called fading gain, is large, then that means this term will be large, right? The good term will be large, and that means this observation will be a reliable observation because most of the energy is coming from the good term. Is that okay? On the other hand, if this magnitude of alpha is very small, so-called deep fade, then that means this observation will be very unreliable because most of the energy of this observation will be coming from the noise, right? Which is unrelated to what we want to detect. Is that okay? So the reliability depends on this fading gain. Okay? The larger the fading gain is, the more reliable this observation would be. That's okay, right? Okay, now you are this combining, diversity combining. You are given L independent observations, right? Independent means each of these observations suffer from independent fading. Some have large channel gain, so they will be more reliable. Some have small channel gain, that means they will be quite unreliable, right? So with selection combining, what you want to do is you only want to pass on one observation from the L observations, okay? You just want to pass on one, okay? So only one survive. So which one would you pass on? Of course, you want to pass on the most reliable observation, right? So, and therefore, so it's very simple. The selection combining metric is simply given by the observation that is most reliable. So what do we mean by most reliable observation? Where I star, the index of the most reliable observation, corresponds to those with the largest channel fading gain. Is that okay? So this arc maximum, we turn the maximizer, the index of the maximizer, okay? Because the one with the largest channel gain means the corresponding observation would be the most reliable one, right? So this scheme is very simple. You give me L choices, L observations. I examine these L choices. I pick the one that is most reliable and pass on to the demodulator. And then I throw away the others. I ignore the others. Okay, so that's the selection combining. So with selection combining, why you can achieve this diversity benefit of increasing your slope? You think of that as a casino game. So what happens is each of these is like you roll a dice, you gamble on big or small, okay? So with L observations, that corresponds to the casino example, is they give you L chances, right? L chances. And then here you are given L chances and you are allowed to pick the most favorable outcome to determine whether you win or lose, right? Okay, if the casino owner is so nice, give you, let's say, two chances. You bet on big, okay? They give you a dice to roll the dice. And then you have two chances, and you pick the most favorable outcome to determine whether you win or lose. Then in this case, what's the chance of losing? The chance of losing is you are so unlucky that in both of these attempts, you lose, right? If you lose on these two rolls, then you will lose, right? So same here. You pass on the most reliable observation to the receiver. So what would be the chance for you to have error? The chance for you to have error would be if the individual error probability is given by this, then the overall error probability will be given by L times. Is that okay? Because this is the same as you need to be, in order for you to be to have error at the end after the selection, you need to be very unlucky that all the observations give you errors. Then, despite the selection, you will still suffer from errors, right? If otherwise, you won't have an error, right? As long as one of these have a good observation, then you won't be suffering from errors. Okay, so it's because of this, it gives you the diversity benefit. This is the exponential of L times. So if you take log on both sides, this L becomes a coefficient. So that's why your slope, this is in log scale. So this is y-axis is log PE. So that's why after taking log, your slope is increased by L times. Is that okay? So this L, after taking log, becomes the coefficient. That coefficient becomes the slope of the line, okay? So this is one simple way to combine the diversity observation. Is that okay? I just pick the best observation, pass on, and then throw away the others. Very simple, right? Now, if you are the engineer, if you're the system engineer, do you see any opportunity of improvement? Let's say someone do it this way. Do you see any opportunity of improvement? Can you do better than this? In order to answer this question, you need to first understand what's the problem of this. What's the disadvantage of this approach? Well, you pick the best observation, right? And pass on. That's something makes sense, right? But for the others, what do? You throw them away, right? But for the others, less reliable observations, are they having zero value? No, they are not rubbish, right? But now what do? You throw them away. So this is a wastage, right? So what you would like to do is, or opportunity for improvement is, if you can make use of other less reliable observation, then you probably will have a better performance, right? So that's the intuition. So What you want to do as an improvement on top of that is you want to be able to make use of all the observations instead of throwing away the others. Okay? So that is the other method called equal gain combining. So in equal gain combining, what you wanted to do conceptually, you want to add up these observations so as to reinforce your good term. Okay? So this is called equal gain combining. You want to add them up. However, you cannot just do y1 plus y2 plus y3, etc. You cannot just add them up literally because each of these observations suffer from a fading coefficient, right? As I said, the fading coefficient as a complex number have two effects. The magnitude gives you the attenuation, which determines the reliability, right? But the phase term, the argument of the complex number in polar format, the argument, gives you a phase rotation. So imagine you are transmitting the S. The S is coming from a 16 QAM symbols, right? So the S at the transmitter side, the signal space is like this, and you have a S will be one of these 16 points, right? 16 QAM, okay? But at the receiver space, after you're passing through the fading coefficient times S plus noise, right? This argument of alpha will represent a random phase rotation, right? The S's are randomly rotated on the receive space. Is that okay? So if you just add up y1 with y2, the good terms suffer from different phase rotation. So if you just add them like this, you are not reinforcing the signal constellation because the S's are randomly rotated. So you'll create AMS. So therefore, before you add up, you need to phase equalize. You need to derotate the S's so that all the observations are aligned on the same basis before you add them up. So what you do is you need to apply this e to minus j alpha 1. This is the phase derotation term times y1 plus e to power minus j alpha 2 times y2, etc. So this term is to derotate the basis. And then after you derotate this, then you add up this with this. That would be the appropriate things to do because in this case, these two derotated terms share the common basis. Okay? So with this equal gain combining, you try to make use of all the observations. You didn't throw them away, right? So that's an improvement on top of this. But then let's continue the discussion. Can we do better than this? Or what's wrong with this? Now here you're adding up all the contributions, right? But you ignore the fact that different observations have different reliability, right? The first scheme, selection combining, recognize that different observations have different reliability. So they make use of that. But the second combining scheme, ignore the fact that different observations have different reliability. So what is the consequence? For example, let's say y2 is very unreliable, meaning that let's say magnitude of alpha 2 is very small, close to 0. Then most of this y2 is actually noise only, right? So what you do by adding up this term is you just contaminate this metric with noise. You get no benefit by adding this term, right? Okay? So the second method, ignore this fact. They just treat every observations are more or less similar, right? So that is basically a disadvantage. So in order to improve on this, the third way is called maximal ratio combining. It's trying to combine the benefit of method 1 and method 2. So instead of doing this sum equally, the idea is you should do a weighted sum, weighted by the reliability. So this is called MRC. It's simply given by the weighted sum, weighted by the reliability. What represents the reliability is the magnitude of alpha. So what you do is the magnitude of alpha 1, E minus J alpha 1, Y1. So do a weighted sum, weighted by this magnitude, plus alpha 2, E minus J, alpha 2, Y2, etc. Is that okay? Now, with this weighted sum, the problem I just described will not exist because now let's say Y2 is very unreliable. Y2 contains mostly noise, right? In this case, this weight would automatically diminish this contribution. right? So you won't just add a purely noise term to contaminate your metric. If Y2 is very unreliable, this weight will automatically get a 0 rate, right? On the other hand, if Y1 is very reliable, this term will automatically get a large weight. Is that okay? And you can further simplify this because magnitude times this e to power minus argument, j argument, is actually equal to alpha 1 conjugate, right? So this can be further simplified into, I write here, alpha 1 conjugate times y1 plus alpha 2 conjugate, y2, etc. So this is just a simplified form. Okay? Now, of course, the way I introduce this is just purely by intuition. You can argue with me, okay, I understand and I appreciate I need to do weighted sum, but why should I weight by this magnitude of alpha 1? Why not weight by a magnitude of alpha 1 square, alpha 1 cube, right? You can argue it this way. So, turns out that this MLC, this particular weighting, is the best way we can weight the observation. So this is optimal. But I save the trouble of explaining to you why this is optimal. You just take my words for this. So this is the best way to do the weighted sum, okay? Meaning that however other ways you dream up to do the weighted sum, your performance will not be better than this. Okay? So these are the three most commonly used methods to make use of these so-called diversity observations before making a decision. Okay? Now, the thing I want to emphasize is, so this is the best, right? As I said, this is the optimal way to combine. But if you combine if you compare the performance, if this is log scale of the error probability, this is signal to noise ratio, also in log scale. The differences in this scheme is like this. These three ways of combining. So this is selection combining. This is MLC. Okay? And the middle one is equal gain combining. The key message is either one of or any one of these combining methods, you can achieve the same slope. That is the first order benefit will be the same. The differences between these different ways of combining is just a horizontal shift. So, and the horizontal shift, as I explained, is a second order issue. So the gap, if I'm talking about, for example, two diversity order, just two statistically identical input distribution, statistically identical diversity observations, we have two of this. Then this gap between the best and the worst is around 3 dB. Why 3 dB? Because the selection combining, on average, you are just using 1/2 of the observation compared to MLC where you utilize both of the observation. So if you look at the signal to noise ratio, this is 2 times of this. 2 times means 3 dB. Is that okay? So this is the comparison. But the important thing is the diversity benefit of having, if I'm talking about two-order diversity, the slope will be doubled compared to this is the case without diversity. This is the case with diversity order 2. Okay? Either one of these combining methods, any one you use, you can already get a steeper slope. So you capture the first order benefit already. The differences between these different combining methods will be the horizontal shift. Is that okay? All right, so this is the answer to the second question. How do we make use of diversity observations before making a decision? Now, before I move on to the next topic, as I promised you last time, I would like to end this topic with giving you a real case study that happens in the Wi-Fi chipset design, I guess 15 years ago. Okay, of course now it's no longer relevant, but at that time it was an important consideration. Again, I guess I told you about the pyramid, right? If you work for a chipset company on the R&D branches, right? There are 3 layers of manpower. The bottom layer will be the developers, right? So usually you need to be a bachelor or master to be a developer. The middle level will be what we call system engineer. The system engineer will be usually PhD, responsible for designing algorithms, right? But the top layer is called the architect, which can be coming from the developer or coming from the system engineer, right? But you need to have a good number of years of experience. You need to be able to comprehend algorithms and understand implementation constraints. So now, once again, let's pretend ourselves to be an architect and then go over the thinking logic. So now, let's say your system engineers tell you about these 3 ways of combining diversity observations. So these are derived from theory or whatever. Going through some analysis, they figure out 3 different ways of generating this diversity metrics, okay? That can translate to performance benefit. And so to the system engineer, this is the output. This is the output. But to an architect, this will be your input, okay? So now let me, so do I have, maybe let me sacrifice this part because after all, we're not utilizing the slide anyway. So let me temporarily freeze the screen. Okay, so I need to explain the background. So now imagine you work in a chipset company designing, it is a real case. So at that time, there was a startup called Apharos selling Wi-Fi chipset. So Apharos was later acquired by Broadcom. So it's now absorbed into Broadcom. So Broadcom now is one of the leaders in Wi-Fi chipset, producing Wi-Fi chipset. But before it was acquired by Broadcom, it was a startup, okay? So at that time, so imagine you work in Apharos. So you're designing a Wi-Fi chipset for the access point. So your task is, so you want to build this chipset solution specialized for access point, because at that time, around middle of 2005, so you know Wi-Fi was originally designed for indoor application. It's just a LAN cable replacement. It's for interconnection of computers in a local area network, right? Within an indoor environment. But now to explain this business model, I need to go back further. So at that time, let's see how far I should date back. Okay, you heard about, at that time there was a very big company in China. It's called Xiaolintong. Have you heard about this company, Xiaolintong? Do you know how it makes money? No? Okay. So at that time, in China, so if you want to subscribe to mobile voice services, okay, you have you only have one choice, is GSM, for example. So GSM, basically, you have a cellular phone that enable you to talk to your friend anytime, anywhere. But the subscription fee for GSM in China at that time was still pretty expensive, a few $100 per month, okay? So now this company, Xiaolintong, think of another technology. They make use of something called cordless phone. So what is cordless phone? You heard about cordless phone before? Or do you know the difference between cordless phone and a GSM phone? Now, cordless phone is actually very similar to Wi-Fi, originally designed for cable replacement for your indoor telephone. So so the cordless phone is usually come with a base. So you install the cordless phone like this. You plug the cable into your telephone socket. So this is a telephone socket, RJ45. Okay. So and then within your home, this base is detachable with the phone. So there is a wireless connection between the base and the headset. Okay. So within your home, you can take the phone without wire, and you can use that phone as a fixed line phone anywhere in the home. You know what I mean, right? So this is called cordless phone. So cordless phone is designed for operating in 2.4 gigahertz. So it's license free, okay? You don't need the license. And then it is originally designed for indoor. So if you compare the technology between cordless phone and GSM mobile, this is a low-cost solution, This is much more expensive. Okay, so you need a license to operate GSM network. Okay, and the mobile phone of GSM is very expensive. And also, you need the installation of the infrastructure, the base station. So everything will be expensive, right? But here, the cordless phone is different. The cost of this cordless phone is very cheap, a few $100s. You can have a base and a cordless phone. This is license-free. You don't get a license. You don't need a license to operate a cordless phone. And the system design is also very low cost, okay? So, but originally, they are for different market. This is for indoor. You buy with the base and the headset. And then this is for outdoor. This is for pedestrian mobility. Okay, so you're just walking in a home, right? You're not on a train or something. This is for vehicular mobility. So because of that, so this is a high-cost solution, this is a low-cost solution. So at that time, around 90s, this company, Xiaolintong, figured out, okay, there is a huge price gap between GSM and other solutions. So what they do is they try to adopt this cordless phone technology. Instead of using the base at home, they try to install the base somewhere outside. Okay, so they install the base on the rooftop of some building. So then the base becomes something like this. And then you just take the headset anywhere you like. Okay, but between the base and the headset is cordless phone technology. That is license-free, low-cost version. So this company basically go and set up the base in a lot of building rooftop and then start to sell their service using cordless phone technology. And then, of course, they charge a very low cost. So at that time, mainland subscribers have two choices if they want to enjoy the benefit of mobile phone services. One, GSM, which is high cost of a few $100s per month. Second, subscribe to Xiaolintong, which is just less than $100 per month. And because of this huge gap, so there are a lot of subscribers who will pick up this low-cost solution, and they earn a lot from this subscription. Okay, and there was a time that it was very wealthy. The headquarters is Hangzhou. Okay, but then in year 2000, around year 2000, so this business model couldn't sustain anymore because the subscription cost for GSM is getting cheaper and cheaper, right? If GSM is getting cheaper, the cost margin, the Xiaolintong's model would be squeezed, right, by this decreasing cost, right? Because if this is just a few tens of dollars, who will subscribe cordless phone, right? People will just subscribe GSM. So because of that, their margin is dropping. So at that time, Xiaolintong was trying to see how they can extend their business model. And then at that time, which is around year 2000, so something happened was instead of wireless voice, people are talking about wireless data, okay, 3G, etc. So at that time, similar situation, if you want to get access to the internet on a mobile phone, one way to get connected to the internet was using a 3G phone, okay, which is expensive. And then Xiaolintong was thinking about, can they use the similar technology? Instead of cordless phone, they use something called Wi-Fi. Now, if you compare cordless phone with Wi-Fi, they are very similar. Wi-Fi, as I said, originally was designed for cable replacement, LAN cable replacement in indoor. But later on, Xiaolintong was thinking about installing the Wi-Fi access point outdoor on the top of on rooftop, so that people using Wi-Fi devices can get connected outdoor as well, in the same way as how they get connected using cordless phone technology. Okay, so that was the motivation at that time. Now, of course, it's everywhere. Now, this is called Wi-Fi hotspot, right? It's everywhere. But at that time, it was Xiaolintong that was thinking about using Wi-Fi on the outdoor scenario. Before that, Wi-Fi was never designed for that purpose. Okay, so at that time, they are looking for a solution to build the access point. Now, of course, if you just buy the access point and install on the rooftop, that's not cost effective because the Wi-Fi access point, you know that is the coverage is only a few hundred meters. Now, with this regular household access point, you will need very high density of Wi-Fi access point outdoor in order for that to make sense, right? But if you have such a high density, let's say every lamppost will have a Wi-Fi access point with this kind of density, what would be the problem? The cost, right? The cost is not about the Wi-Fi access point. The access point is just a few $100s. It's nothing compared to a base station. But the cost is, in order to install your access point on a rooftop or on a lamppost, you need to pay the real estate cost. And this real estate cost is the major overhead. So therefore, at that time, in order for that business model to work, they need to have an access point specially designed for outdoor with extended coverage of the order of few kilometers, okay? So that they can decrease the density of the access point, okay? So that was the motivation. That was the demand. So at that time, let's say you are working in Aferos, in the R&D team. Your task is to design a chipset solution specialized for outdoor access point application. That means you need to have extended coverage compared to your competitors. Is that okay? Okay, so that's your task. Now you are the architect. Now you go through this analysis. You figure out the reason that the access point in the market have this limited coverage is because of fading, because of this flat fading, right? Because of this flat fading, the one-star trouble is the error probability fall off slowly, let's say like this. So if you want to achieve a certain target error probability, let's say 10 to the power minus 4 for your data application, you need this amount of signal-to-noise ratio, right, which is pretty high, 40 dB. With 40 dB, that means the maximum path loss between the transmitter and the receiver would be very small. And that translates to a few hundred meters of coverage. Is that okay? That was a problem. So how do you extend the coverage of your solution? Okay, you study this course, so you know the solution roadmap is diversity. Okay, you need to exploit diversity. So what kind of diversity can you exploit? Let's say you go through link budget analysis. You figure out, okay, diversity order of 2 would be sufficient, right? With 10 to the power minus 4, if you have diversity order of 2, the signal-to-noise ratio reduces to 25 dB. So let's say with 25 dB signal-to-noise ratio, you got 15 extra dB in your path loss. And that 15 extra dB translates to, let's say, 1 kilometer coverage, which will be sufficient for your application. Okay? Let's say it's something like this. So then the next step is, how do you create 2 diversity observations? How do you create 2 diversity observations? As we study, right? So it can be coming from time, frequency, or spatial, right? But at that time, this was a startup, right? So, and then time diversity, frequency diversity have the spatial efficiency penalty of 50%. This is not good, right? Moreover, if you want to engage in time and frequency diversity, you need to change the standard. You need to change the Wi-Fi standard. So this is not suitable for a startup, okay? And then you go through all these options. You figure out, okay, receive spatial diversity would be an attractive choice, right? Because receive spatial diversity can achieve 2-order diversity without any throughput penalty. And it is transparent to the transmitter. That means you don't need to change the standard to adopt this solution, right? So therefore, you decide to go for receive spatial diversity. Now, and before I talk about the receive spatial diversity, I need to talk about the baseline solution in the market. The baseline solution in the market would be like this. Now, for a Wi-Fi chipset, you have a receive antenna. What you receive is an RF signal, 2.4 gigahertz carrier frequency, right, from Wi-Fi. And then you don't directly process this RF signal, which is a bandpass signal. What you need to do is you need an RF chipset. The job of this RF chipset is to do down conversion into the baseband, right? So after the RF chipset, this becomes a baseband signal. Is that okay? Now, but of course, this baseband signal is analog. You don't just process in the analog domain. You usually, for example, the minimum distance demodulation, blah, 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 all this receiver processing would be implemented more conveniently using digital processing, right? So therefore, you would need to go through this ADC conversion, analog to digital conversion. This becomes a baseband digital. Okay, and after that, you go through the receiver processing on this is what we call baseband processor. This baseband processor, in the case of a Wi-Fi chipset, is an ASIC. Okay. Okay, but you can imagine this can be a DSP, this can be an FPGA, whatever. So this is doing baseband processing. So this is your baseline chipset solution. Your competitors is basically in the market at that time. Most of the Wi-Fi chipset have these three essential components. And these three essential components, they are a major cost item. Each of these is expensive. Okay, so that would be the baseline solution. Okay, so this solution, because as I talk about, you don't have diversity. So therefore, the coverage for this kind of, if you build your access point using this baseline chipset, your coverage is just a few hundred meters, okay, which will increase the cost of your infrastructure. The whole business model would not work. So you want to design a chipset solution so that you can provide extended coverage for your access point, okay, for the access point that use your chipset solution compared to your competitors, okay. So you go through all the study, you know that you want to achieve two-order diversity. So in this case, and for the reason I have explained, right, you want to have the two-order diversity coming from receive spatial diversity. So you have two receive antenna. Okay? With these two receive antenna, the first receive antenna pick up first observation. The second receive antenna pick up a second observation, right? But they are in RF format. Bandpass signal at 2.4 gigahertz carrier frequency. Is that okay? That is your input. Now you are the system architect. So what do you do next? What do you do next? Well, as I said, right, this is the RF signal. You cannot process RF signal directly. So similar to the baseline solution, you need to have the RF to do down conversion to the baseband. And then similarly, for the second observation from the second antenna, you need another RF to convert to the baseband signal, like this, right? Then what do you need to do next? For the same argument, these are analog domain. You don't process the receiver based on the analog domain. You need to convert to digital domain. So you need ADC for the first path and ADC for the second path, so that you have the digital baseband signals from the two receive antenna data path. Is that okay? Then, after you have this, then you have the baseband processing. For example, the diversity combining, whatever, can be implemented in the baseband, right? So that would be a naive way to implement two-order receive spatial diversity. Now, what's the problem of this solution, of this architecture? If you're the system architect, could this be your solution? What's the major issue? Cost. Because if you look at this cost unit, you are talking about each of these is expensive, right? Your baseband, your baseline competitor, the solution is like 3 cost unit. Now, with this advanced solution, you are talking about 5 cost unit, right? Almost double the cost. Now, in the chipset business, every cent count. Okay, so if your solution is double the price, like this, you won't sell at all. Okay, so now you are the system architect. What can you do? Now, of course, you need to think of some other way to have a reduced cost solution, right? So what are the potential opportunity for you to reduce the cost? Now, in the context of this, right, so your system engineer give you these are the 3 combining methods, right? So let's say you know from your system engineer that this maximum ratio combining is the optimal, right? So this is the best performance. Now, let's say we tried the best performance. If I have to generate this metric, right, MLC metric, what do I need to know? You use this formula, right? Now, assuming I know the alpha 1, alpha 2. So this alpha 1, alpha 2 is coming from channel estimation, which we'll talk about. So let's say you know about this alpha, this fading coefficient. So if you try to compute this metric, what do you need to know? Of course, you need to know the y1 and y2, right? You need to know the y1 and y2. So the first question you should ask yourself is, where would you like to compute this metric? Would you like to compute this metric in the digital baseband or in the analog baseband? Compute this equation. Now you just ask yourself, right? Imagine the baseband is a DSP. If I ask you to write a C code to implement the solution, I guess any one of you can do it, right? It's just one line. But if I ask you to build analog circuit to compute this, it's not that trivial, right? Okay, you have to start from using transistor and filter and whatever to build this. So obviously, you prefer to compute this in the digital domain, right? Now, so if you compute, let me use this. If you compute this MRC here in the digital baseband, so that means what do you need to provide to this MRC? You need to provide this MRC with Y1 and Y2, right? So where are these Y1 and Y2 coming from? This is your Y1, this is your Y2, right? If you need Y1 and Y2 from the digital baseband, so this digital baseband of Y1 and Y2 are coming from ADC, right? So that means you also need two ADC to generate Y1 and Y2 digital version. If you need Y1 and Y2 analog in the analog domain, that means you also need two RF chips, right, to generate Y1 and Y2 baseband analog signal. So that means if you compute the MRC here, you naturally would need the full RF and ADC chain for each of these antenna. And then you need to pay 5 cost units. And that solution will not fly, will not sell. Is that okay? So now, okay, so suppose I want to give up my performance a little bit. Just keep in mind, the good thing about any of these combining methods can give me the first order benefit of the slope. So I capture the full benefit of the first order diversity protection, right? The difference is just a horizontal shift, which is a second order gain, okay? So if I sacrifice a little bit, let's say I use equal gain combining. So I follow the same logic, right? Where should I compute this metric, equal gain combining? Equal gain combining is talking about this equation, right? Still, I prefer to compute this in the digital domain, right? Right? If I want to compute this in the digital domain, that means if this becomes equal gain combining, what do I need to know? I also need to know Y1 and Y2. So there is no difference. There's no difference compared to MLC in this perspective, right? Okay? So if I compute this, I would rather compute this, right? Because this will give me better performance at the same cost. So, okay, so at this point, this back of the envelope analysis will give me the conclusion. If I want to compute this or compute this, I will need the full RF and ADC chain, 5 cost unit to implement this solution, right? What about this, selection combining? Well, go through the same logic, right? Where should we compute this? Of course, you can compute this in the digital domain, right? If I ask you to write a program, a C program to compute this, you can imagine the C program will be just a bunch of if-then-else statement, right? It's a selection process. You just have a case switch statement. We'll be able to implement this solution, right? So since this is, in terms of data path, there is no computation involved. It's just a selection, right? So I can compute this in the digital domain. But if I compute this in the digital domain, I would still have to pay for this 5 cost unit to get me the Y1 and Y2. But if I do it this way, so let's say this is the selection combining. If I compute this in my digital baseband processor, I will still need to have Y1 and Y2, right? To get Y1 and Y2, I will need the full ADC and the RF chain. But you think about this solution, it's very, very suboptimal because you need to pay the cost to get Y1 and Y2. Once you get Y1 and Y2, what do you do here? You pass on one and throw away the others, right? And these others you throw away is not free. It's quite expensive, right? So by implementing it here, this is very wasteful implementation. You pay a lot of hardware costs to generate Y1 and Y2, and you throw away one of this, right? So this is not good. So instead of implementing this in the baseband, can we implement this in an analog domain? Potentially, yes, right? Because what is this? after all, the selection is just a switch, right? If this is a switch, implementing in analog domain with a switch is not too bad, right? Okay, basic electronic circuit, if you studied EE before, you should know how to build a switch, right? Is that okay? So you can implement this in the analog domain here, baseband. Well, then you try to push it further. Can you implement this selection in the RF directly? The question is the same as asking, do you have an RF switch, right? It turns out there is some low-cost RF switch. It's called pin diode, okay? If you're those working on the RF circuit, you should have heard about this. It's pin diode. So the switch can also be, there's a low-cost switch in the RF front end as well. Now, if that's the case, then I don't need to implement here, which is an expensive solution. I can implement the selection up to here, right? Now, if I implement the selection up to here, so then my entire data path could be like this. I could have a switch, right? So this is implementing the selection combining. This is a 2-to-1 switch, right, in the RF. After I selected the observation from the first antenna or the second antenna, then I need just one RF to do down conversion to the baseband. And I just need one ADC and then one baseband. Is that okay? So if I can push the switch, the selection process, the selection data path to the front end, I just need 3 cost units to implement this advanced solution. Can you see that? And then I can take advantage of this diversity protection, achieve an extended coverage, right? So that's the good thing. So we can see an opportunity. By sacrificing the performance a little bit, by sacrificing 3 dB gap compared to MLC, I would have an opportunity to save my cost unit significantly. Is that okay? Now, but that's not the end. This is just a sketch of the idea. There's still something we need to consider. This is the data path. We also need to figure out the control path. Now, what do I mean? How do you drive this switch? Remember, what's the principle of selection diversity? We want to pass on the most reliable observation, right? What do we mean by most reliable? The observation with the largest channel gain, right? Okay, we cannot randomly choose a switch, right? If we do random selection, the diversity protection is gone. We must set up the switch, control the switch so that it's passing on the most reliable observation, right? So to determine how do I know which one is the most reliable observation? I need to know alpha 1 and alpha 2 first, right? So this involves something called channel estimation. So to explain channel estimation, I need to explain the frame structure of Wi-Fi. So typically in Wi-Fi, a frame structure is like this. A frame consists of 3 parts. And this is called preamble. So Wi-Fi packet, unlike cellular system, Wi-Fi packet operates on a frame-by-frame basis and is self-contained. Okay. In cellular system, it's different, as we'll talk about in the next chapter. In cellular system is contiguous. That means one frame follows with the others, back to back. But in Wi-Fi, it's not. After you send one frame, you need to wait for a random time before you can send next frame. So every frame will be self-contained. Okay. And each Wi-Fi frame consists of 3 parts. This is called a header. This header contains information about the modulation level, the payload length, etc. Okay? And then this is a payload, the passengers. And then this preamble does not contain any useful data. These preamble are just the reference symbol. You just assume, okay? Assume they are all 1. So you have n such preamble symbols. They are all 1. Now in practice it's not 1, but for easier explanation, let's assume they are set to be 1, okay? And you have n such symbol. So this preamble is used for the receiver to enable the receiver to estimate the channel. Why do I say this? You just take the nth preamble transmission, the observation, from the n preamble transmission is given by alpha times the SP. SP is the preamble symbol plus the noise, right? Is that okay? Now, unlike the data transmission, the data part is the unknown. But now this part is known, so we set it to 1, okay? The unknown is the channel. Is that okay? So now you are the receiver. Based on this observation, you can still estimate the unknown channel by this observation, right? So how do you do a channel estimation? An easy way to do that is the estimated channel by the receiver will be simply given by, if I have n such symbol, 1 over n summation, just take the mean. And that can give me the estimate for the channel. Is that okay? And by the way, this is called least square estimation, channel estimation. Is that okay? So this is intuitively very simple. Each observation is equal to alpha plus noise, right? So this is like I give you 100 observations, and you want to estimate the mean behind these 100 observations. What do? You do arithmetic mean, right? So as simple as that. So this is how a receiver estimates the channel. So where would you compute this channel estimator? Analog or digital? Of course, digital, right? If I ask you to write the C program to compute this, is just a piece of cake, right? If I ask you to build analog circuit to compute this, this is another not that trivial. So you want to compute this channel estimation, so at the baseband, okay? So that means it's the baseband that can estimate this alpha 1 and alpha 2. And based on this alpha 1 hat and alpha 2 hat, you can drive the switch, right? So this is the control path. Is that okay? That's the logic. Once the baseband estimated alpha 1 hat and alpha 2 hat, you can use this knowledge to drive the switch. For example, if the magnitude of alpha 1 hat is larger, then that means Y1 would be more reliable than Y2. Then you should set up the switch in the first position. Is that okay? Now, but the problem is, it's still not the end. The problem is, how do you estimate alpha 1 hat and alpha 2 hat? The transmitter just transmit the Wi-Fi frame like this, okay? And now you only have one RF and ADC frame, ADC chain. Okay, that means at any time, you can only pass on the signal from one of these two antennas to the baseband. The baseband use this to estimate the alpha, right? So use this preamble observation to estimate the corresponding alpha. But for example, if the switch is in the first position, then during this preamble, during this entire period, this one, the switch being in the first position, can only pass on the observation from the first receive antenna to the baseband. And if that's the case, the baseband can only estimate alpha 1 hat, right? Understand? Because throughout these n preamble symbols, the switch position is in position 1. So therefore, all these preamble observations would be coming from the first receive antenna. If they are coming from the first receive antenna, behind this preamble observation, they only contain alpha 1. And then using this least square estimation, you can only estimate alpha 1, right? You cannot estimate alpha 2 because you have no observation. Understand? Now, if the switch is in position 2, the same happens because you only have one RF and ADC chain. Then the baseband input to the channel estimator, if I call this channel estimator, the input to the channel estimator will contain alpha 2 only, right? And then you follow this channel estimation, you can only get alpha 2 hat. Is that okay? But you need to know alpha 1 hat and alpha 2 hat before you know how to configure the switch. Then what do you do? What do you do? Now, if you cannot figure out the control path, then the solution wouldn't work, right? Because we know that the switch cannot be randomly selected. We need to select the switch so that it passes on the most reliable observation, right? It cannot be random. And in order to configure the switch at the appropriate position, you need to know alpha 1 and alpha 2. But because you only have one RF and ADC chain, at any time you can only pass on one observations from the two antenna observations. So that means you can either estimate alpha 1 hat or alpha 2 hat, but not both. Then how do you resolve this dilemma? Any idea? Do you understand the problem here? The problem is if the default position of the switch is in position 1, then all this observation feeding into the channel estimator will only carry alpha 1 here. Then this channel estimation can only give you alpha 1 hat, right? If the default position of the switch is in position 2, then the preamble observation will only contain alpha 2 here. And then using this channel estimation, you will only get alpha 2 hat. But what you need is you need to have alpha 1 hat and alpha 2 hat simultaneously. Then how can you fix it? Now, this is a challenge, but this is also an opportunity for innovation. This is a good thing if you can find a solution, because your competitor cannot easily think of. Now, if this is trivial, then your competitor can easily think of this solution, right? Then you may not have a technical edge. So this is not a straightforward implementation. There are some challenges in the control path you need to overcome. And if you can overcome, then that will be a good opportunity for your unique innovation. And that would also be the technical barrier against your competitors. So any innovative ideas? Any possible way out of this dilemma? How can we simultaneously estimate alpha 1 hat and alpha 2 hat so that we can configure the switch to pass on the most reliable observation? Well, the thing is, this is a preamble with n preamble symbols, right? Okay. So now we know at one time we can only estimate alpha 1 hat or alpha 2 hat. So how can I get alpha 1 hat and alpha 2 hat? So one idea is, how about I partition this into if I partition this preamble into two periods. Let's say this is T0, this is T1, this is T2. Okay, let me define some timing. So between T0 and T1, let's say my switch is in position 1. Then with this configuration, using the least square estimate I just erased, I can get alpha 1 hat, right? Because all the preamble observations are coming from the first receive antenna. So it naturally carries alpha 1. Is that okay? And then from T1 to T2, I configure the switch to position 2. And in this case, this input to the CE will be coming from receive antenna 2. So it will contain alpha 2, right? Then I will have alpha 2 here. Is that okay? So at the end of T2, the baseband will be able to get alpha 1 hat and alpha 2 hat simultaneously. And then at this point onwards, from this point onwards, I will be able to know which one is the most reliable path. Suppose alpha 1 is most reliable, okay? Alpha 1 hat magnitude is larger than alpha 2 hat magnitude. Then from T2 onwards, I have the switch in position 1. So that the payload, the header and the payload can benefit from this selection combining. Is that okay? So that would be the solution to the control path. You basically divide the preamble into two halves. The first half, you configure the switch so that the data path will give you observation from the first receive antenna so that you can estimate alpha 1 hat. And then in the second half, you configure the switch to the second position so that all the preamble observations will be coming from the second receive antenna. And then you will be able to estimate alpha 2 hat from that. After that, you'll know alpha 1 hat and alpha 2 hat, and then you will be ready to configure the switch to the most reliable observation. Okay, so the rest of the frame will be able to benefit from this selection. Is that okay? So indeed, this is an innovative solution. And then there are patterns around this idea. And that would basically be an entry barrier to your competitor. So this is the job of an architect. Now you can see as a second example. So to the system architect, these equations are just your input. You need to map these equations into some implementable architecture, and moreover, you have cost constraint and other implementation constraint. Out of this constraint and the equations, you want to figure out something that is viable. So that's the art of being an architect. Is that okay? Now, I'm not sure if you're interested in this kind of thinking or not. So not everyone can be a good architect, right? But if you find yourself very interested in thinking about these details, then you can have a good potential as a future architect. But on the other hand, if you find this kind of too tedious, right, then fine, you can be a system engineer or you can be a developer. Okay, that's also okay. Is that okay? Now, if you think that it is okay, let me further ask you. Now, so now what you have achieved is similar cost unit as your competitor. Okay, three major cost unit as your competitor. So but then you enjoy the benefit of the second order diversity, so that your coverage, if the access point is built based on this your chipset solution, the access point will have an extended coverage compared to your competitor. So this is nice, right? But so if this works, so right now we just have two order diversity, right? Can we extend this to four order diversity by installing 4 antennas instead of 2 antennas? You know, antennas are just a piece of metal. It costs nothing, right? You only need one RF and ADC chain. If you can use one RF and ADC chain to couple with 2 antennas, how about 4 antennas? Can you still use the same architecture to deal with 4 antennas? If you have 4 antennas, that means you are achieving a diversity order of 4. Your slope is increased by 4 times like this. You get even extended coverage, right? So that's the motivation. Can you do this with 4 antennas? If you say yes, then I ask you, can you do this with 8 antennas or 16 antennas? So you know by intuition, somewhere down the road, there should be some number of antennas that it won't work anymore, right? So what would be the issue or bottleneck? If I keep on increasing the number of receive antenna with the same cost unit, why it will not work? Which part will break down? Understand my question? Now, what I'm asking, I don't mean I will test you this way, but this is another example that I can ask you in the examination, right? So I will keep drilling deeper and deeper about a solution. Or you can think of that in the setting of a job interview, right? If you interview for a chipset designer, then when we talk about this particular design, right? If you got a chance, if I were the interviewer, I would definitely ask you on this. Okay, so what about 4 receive antenna? What's wrong with 4 receive antenna? Which part will eventually break down? So with 4 receive antenna and 1 RF and ADC chain, how should we design the control path? I need to estimate alpha 1 head, alpha 2 head, alpha 3 head, alpha 4 head, right, in this case. So how should I do this? Using similar logic, right? I need to partition the preamble into 4 pieces, right, in this case. And each piece will have a switch configuration to estimate the alpha I head, right? So what's wrong with that? If I have 8 receive antenna, I just partition this into 8 pieces, right? But can I keep on doing this? Remember, the channel estimation, let's say alpha I hat, is given by 1 over Ni summation I from 1 to Ni YPI, right? Why do I need to take the average? I take the average to enhance the quality of the estimation, right? If I only have one observation, right? This observation is a noisy observation of the mean, right? then you don't have the chance to take the average. Then what can you have? You just have you just take the observation as the alpha. In this case, your alpha hat will be very unreliable, right? Contaminated by noise. But if I have 100 of this observation about the mean, after you take average of 100, your signal to noise ratio will be enhanced by 100 times, right? Okay. So therefore, this averaging, the purpose of this averaging is to improve the quality of this channel estimation. Is that okay? Now, in the standardization of Wi-Fi, this preamble have a certain n. I forgot the number. But this n, this is an overhead, right? So there is a reason that the Wi-Fi standard requires this number of preamble symbols, right? Okay, because otherwise it's an overhead. If you do not need this number, they will, of course, shorten it in the frame, right? So you partition this preamble into two halves, you're already stretching the limit. Okay, you're already cutting the corners. By partitioning this into two halves, the quality of this alpha hat compared to without partitioning, the quality of the signal to noise ratio of this alpha hat will be 3 dB worse, right? Okay. So if you continue to partition into four pieces, then this quality will be 6 dB worse. So eventually, if you keep on doing this, this alpha hat will be so unreliable that it is not related to the actual alpha. Now, if you're doing the selection of the switch based on some random alpha, then you are not enjoying the benefit of diversity anymore because you are essentially doing random selection. You understand my point? So the basis for this diversity benefit is you are doing a selection based on a reliable channel estimation. And so therefore, reliable channel estimation requires some kind of averaging here. If this averaging numbers, the numbers you want to do, you can use for averaging is getting too small, then this alpha hat will not be reliable. And then yes, it appears that you are selecting the switch configuration after T2 based on this alpha 1 hat, alpha 2 hat, alpha 3 hat, alpha 4 hat. But if this alpha hat are so unreliable, you are essentially like doing a random selection. If you do random selection, you lost all the diversity benefit. You won't have the slope benefit anymore. Is that okay? So if I really need to have 4 receive diversity, then what can I do? If I really, after the link budget analysis, I really need to have 4 order diversity to make up, to have that coverage target, to meet that coverage target, then what can I do? Then in that case, I have 4 receive antennas, but then I may need to have 2 RF and ADC chain, so that I still partition the preamble into 2 halves. In the first half, with these 2 chains, I will be able to estimate, I don't know, alpha 1 hat, alpha 2 hat. In the second half, I will be able to estimate alpha 3 hat, alpha 4 hat. Is that okay? So things like that, okay? So of course, at that time, the chipset solution only have 2 receive diversity. That will be sufficient. Because at that time, this is the cost unit, right? So you don't want to sell the solution too expensive. So therefore, with this, you cut corner by partitioning the preamble into 2 halves, and therefore you already suffer from 3 dB penalty. So you don't want to further partition this, and you don't want to increase the cost unit by too much. So at the end, you end up with 2 receive antenna. That will pretty much give you the optimal trade-off. Is that okay? Now, of course, I said that was the past. Now, all the MIMO chipset with the advanced standard 11N, they are all already equipped with MIMO. They are already equipped with multiple RF and ADC chain. Okay, so that is no longer an issue because your baseline solution in the market is already having this multiple RF and ADC chain. Okay. All right. So this is although this is 1 page, it took me quite some time to elaborate the solution. Okay. So this is the 1-star trouble. Once again, the 1-star trouble is the error probability curve falling off slowly. And whenever you hit this 1-star trouble, always think about diversity. Diversity is your solution roadmap. The question is, how can you generate diversity observations? It can be from time, frequency, and space. Different implementation constraint will drive you to some of the dimension may not be feasible. Okay, so that is one design space. Where do you create diversity observations? From time, from space, from time, from frequency, or from space. For space, should you do it over receiver or should you do it over transmitter? These are the design space. The second design space is the combining method. I explained 3 combining methods, right? But Again, depending on your implementation constraint and situation, you may have to exercise your judgment on which combining method you should use. Okay, so it's never about the computational overhead. Somebody will say, this advantage is the computational complexity is less compared to this. Now, this is third order or fourth order. The reason is because if you really think about implementation, you already pay the cost of a baseband processor. Let's say this is a DSP. You already paid for the DSP cost. Whether you use it to compute something or not, it's still there, right? This is a sunk cost. You understand what I mean? You use it to compute something more complicated like this, or you use it to compute something less complicated like this, doesn't make a difference at all. Is that okay? So the issue between this and that is not just about computation complexity. That's some naive way of looking at things. The real difference between this one and this one is actually on the impact on the architecture, on the data path and control path. Okay? I almost forgot about the break. So I guess this is a convenient point to have a 15 minutes break. And after that, we come back to talk about the two-star travel that we talked about a while ago. Okay? Okay, let's resume. All right, so now let's look at the second case where I call this the 2 stars of trouble. So let's look at what exactly is the trouble. So this second scenario is what we call frequency selective fading channel. So the condition is the transmission bandwidth is much larger than the coherence bandwidth, okay? Or equivalently, that means the delay spread is much larger than the symbol duration, okay? So what happens is, as I explained last time, if you transmit one symbol, let's say this is your symbol. Now in this case, you are affected by, let's say, 1,000 physical multipath, and each path landed at the receiver with a different delay, right? But now the delay spread is much larger than the symbol duration. And last time I introduced the concept, number of resolvable symbols is given by the ratio between the delay spread and the symbol duration, or the ratio between the transmission bandwidth over coherence bandwidth. take the ceiling. Okay? So for example, if the delay spread is like 4 times of the symbol duration, so that means after you transmit this symbol over the multipath, let's say 1000 physical multipath, the earliest, the first path maybe give you a symbol here, and then added with the 1000 path may end up having a delay, I don't know, 4 times of that. Okay, so this delay and this delay, this range would be 4 times the symbol duration. Okay, so in this case, you have a much larger delay spread than your symbol duration. So after you add up all this together, you will see that the received signal will be like perceived as multiple symbols suffering from independent fading. For example, this is suffering from the first fading coefficient alpha 1. This is alpha 2, alpha 3, alpha 4. These are random. Okay, this is like conceptually when you talk to yourself over a outdoor landscape with this acoustic refraction. Then when you say a letter A, you may hear your own voice as A, 4 distinct echoes. Okay, so that would be the acoustic analogy of this phenomena. Okay, so that would basically be the so-called frequency selective fading channel scenario. So mathematically, that means if you transmit a symbol xt, what you receive would be a superposition of these L resolvable symbols plus the channel noise. Okay, so this is in contrast with flat fading channel. In flat fading channel, when you transmit a symbol, you perceive as one resolvable symbol at the receiver plus noise. Okay, so now this is an extended version. When you transmit one symbol, you perceive as multiple resolvable symbols. Each of these perceived symbols will suffer from independent fading. It will be something like this, plus the channel noise. Okay, so now you may say that there's no big deal about this, right? So if you say a letter A, you transmit one symbol, you perceive as 4 copies, right? So that's okay. However, well, let me explain the 2-star trouble. Let me erase this. Now in this case, if you try to plot the error probability curve, this is error probability, this is signal to noise ratio in dB. Now we say that if you transmit, let's say, I don't know, BPSK modulation, this will be BPSK on flat fading channel. Okay, so the penalty, the 1-star trouble, was that this error probability curve falling off slowly as you increase the signal to noise ratio, right? That means you need to increase the signal to noise ratio by quite a large amount in order to have a mild reduction on the error probability, right? So that was the 1-star trouble. But now if I try to plot the same scenario, same BPSK modulation and demodulation, but now over this frequency selective fading channel, the error probability curve will be like this. So initially, it will be falling off slowly, similar to the 1-star trouble case. But gradually, as you further increase the signal to noise ratio, gradually the error probability will be like this. So this will be BPSK over frequency selective fading. Okay? So the 2-star trouble are coming from first, your error probability is still falling off slowly, similar to the flat fading case. But the 2nd star is here. You have something called irreducible error flaw. So despite, even if you do not mind the extra signal to noise ratio, you won't be able to push the error probability to any level you like. Now, so this irreducible error flaw may or may not matter, depends on what is your target error probability. If your target error probability is here, then that means you do not need to operate into this irreducible error flaw region. So the presence of this error flaw doesn't affect you at all. You just need to operate in this region. So you can treat it pretty much like the flat fading case. But most of the time, you will not be that lucky. Most of the time, your target error probability will be below the error flaw. Now, when this is the case, you cannot ignore this irreducible error flaw. You need to think of some way to deal with this. Okay? And that's the two-star trouble. So you can see that it's more challenging compared to the first case of flat fading, frequency flat fading channel. Okay. Now, before I talk about solution, so this is the nature of the two-star trouble. Before I talk about solution, we need to explain why we have this irreducible error flaw to start with before we can talk about the solution. Okay. So to explain this irreducible error flaw, let me take an analogy. Again, the acoustic analogy. Suppose these are the two outdoor cliffs facing each other, okay, and they are widely separated. And this is you. You are talking to yourself. You transmit the letter A. So your voice will get bounced back and forth multiple times. Let's say bounced back and forth 4 times, so that your receiver, you will hear yourself as like A, 4 distinct echoes like this. Okay. So as I said, there's no big deal about this, right? So you just receive your voice 4 times. So far, so good. So yes, there's no big deal if you're just singing 1 time. But if you start singing a song, then it's a different matter. If you start to say A, B, C, D, E like this, then each of this transmission will end up having 4 echoes like this. Then they will overlap with each other. They will contaminate with each other, mess up with each other. Okay? So for example, if you look at this 4th time slot, you think of this 4th time slot as a steady state. Okay? Let's consider the observation model for the 4th time slot. Let's say Y4, denoting the 4th time slot observation. This Y4 consists of multiple copies, right? Alpha 1 times the immediately transmitted symbol D, okay? So times D, plus alpha 2 times C. C is the previously transmitted symbols, right? Plus alpha 3 times boy, plus alpha 4 times A, and then plus noise. Is that okay? So that would be the composition of this observation, Y4. So again, we analyze from this composition, we try to identify which terms are good, which terms are bad. Now, since this is a 4th duration, so let's say our target is to detect for the transmitted symbol D, okay? So in this case, this is a good term because it contains the information we want, right? And then these are bad terms, right? They are bad because they do not contain anything related to the information D, okay? They are just contamination of your observation, right? Also, the noise, of course, will be bad. But we tend to discuss this separately. This term is called interference, or we call this inter-symbol interference, because they are coming from the echoes of your previously transmitted symbols. So you're interfering yourself in a way, okay? So they're called ISI, inter-symbol interference. The noise, of course, is the background noise, which is bad, right? It's a contamination. Okay, so the observation in the 4th time slot consists of a good term in the presence of 2 bad terms. One is coming from your self-interference. The other is coming from background noise. Okay? Now, of course, we can see that the error probability depends on the quality of this Y4, right? The quality of Y4 is basically the power ratio of the good term over these 2 bad terms, right? And we have a term for this. This is called SINR, signal to noise plus interference ratio. This is simply the numerator is the power of the good term. That is the power of this term, right? So the power of this term is alpha 1 squared times the transmission power for this symbol. Is that okay? And the denominator is the power of the interference and the power of the noise added together. So what's the power of this interference term? You take the square of this, right? So it will be alpha 2 squared plus alpha 3 squared plus alpha 4 squared shared by the same transmission power, okay? Because you have the same transmission power for your previous symbols as well. Plus the noise power. The noise power is N naught W, right? So that would be the so-called signal to noise plus interference ratio. The larger this ratio is, the more reliable this observation would be, and therefore the smaller the error probability would be, right? Okay? So error probability depends on this guy. So now let's observe what's the behavior of this SINR. Now I mentioned usually we would like to separate the discussion between the interference and noise, right? But you may wonder, they are both bad terms. Why don't we lump them together and discuss it all together? From this, you see that they have very different behavior. The first order, what's the first order difference between interference and noise? From this, you can see that this interference term scale with the transmission power, right? This is the interference power proportional to the transmission power. Whereas the noise power is independent of your transmission power. Can you see that? Okay, this is like, if you think about this classroom as an analogy, when I'm talking, you hear my voice, which is a good term, hopefully, plus the background noise, right? If I'm not talking, you still hear the fan noise, right? Would the noise power, fan noise power, depending on how large the power I transmit? No, right? Even if I'm shouting, the fan noise power is still the same. Okay, so that's the background noise is always having a constant power, independent of your transmission power. However, the interference power, they are coming from your previously transmitted symbols. So if you double your power, your transmission power, this previously transmitted symbols power would also be doubled. Is that okay? So that's the first order difference between interference and power and noise. Interference power tends to scale with your transmission power, whereas noise power doesn't scale with your transmission power. Okay, keep this in mind. That's the key difference. And that's why, because they behave differently, we need to separate the discussion between these two. Okay? So so overall, this is the signal to noise plus interference ratio. So let's try to analyze the behavior of this in two regions. The first region is when the transmission power is very small. The second region is when the transmission power is very large. Let's see how it will behave. Now, so let's look at one extreme. So if we have small transmission power, in the small transmission power, there's one term in the numerator that is not affected. But in the denominator, we have two terms, right? One is ISI, one is the noise power. When transmission power or the signal to noise ratio is very small, then what can we say about these two terms? Which term is more significant? Of course, this term is more significant, right? Because you can make this interference power arbitrarily small by considering a small enough PS, right? So in this case, this SINR behave like this, because you can ignore this term in the denominator. Is that okay? Now, if you look at this, this is like the signal to noise ratio in the flat fading case, as if you don't have this interference, right? When you don't have this interference, this reduces to the flat fading case. So that's why in the small SNR region, the error probability curve behaves very similar to the flat fading case. Okay? Because the SINR essentially reduces to the SNR in the flat fading case. So the two curves behave very similarly. Okay? Now, what about the other extreme, large signal to noise ratio? When the power, transmission power becomes arbitrarily large, ask you the same question again. In the denominator, which term becomes the important dominating term? In this case, it's this interference power, right? Because you can make this term arbitrarily large relative to this constant. So in this case, we can ignore this noise term, right? When we do this, then this SINR becomes what? If I ignore this term, this power in the numerator cancels with the power in the denominator. So that means this SINR will be saturated to a constant level. Let's call this beta, which is the ratio between this guy and this guy. Is that okay? So that means this SINR becomes independent of your transmission power gradually. Okay? So therefore, that's why you have this irreducible error floor, because the SINR will no longer decrease as you increase the transmission power. Is that okay? So that's the fundamental reason you have this irreducible error floor. So we give a name for this. This region, when the transmission power or signal to noise ratio is small, we call this noise limited region. Because the bottleneck is the noise in this region. So we call this noise limited region. Okay? The behavior would be very similar to the case as if there were no interference. The performance is limited by noise. Okay? On this other extreme, we call this interference limited region. Because in this second region, when the transmission power is arbitrarily large, the performance bottleneck is no longer determined by the noise. The performance bottleneck is this interference power. Okay? So that's called interference limited region. And the two behavior will be very different. In the interference limited region, the bottleneck, as its name implies, the bottleneck is the interference, right? The noise doesn't matter. Okay? Whereas in noise limited region, the bottleneck is the noise, as if there were no interference. And that explains why the error probability curve will have this behavior. Okay? And from this analysis, we can also see that this level of the irreducible error flow depends on what? It depends on the channel memory. Okay? So in my example, I have 4 channel memory. When I say a letter A, you receive as 4 distinct echoes, right? So, but in the case of the channel memory being not 4 but becomes 40, then that means this beta will be, you have 39 terms in the denominator, right? So that beta will be even smaller. And in that case, the error flow would even be higher. Is that okay? So this error flow depends on the channel memory. Depends on, I erased that, the number of resolvable symbols. Okay? The larger the resolvable symbols you have, the higher the error flow would be. Okay? So that would be basically the qualitative understanding of this 2 stars of trouble. All right? Now, when you have flat fading case, like this, we say that this is the 1-star trouble, the error probability falling off slowly as you increase the signal-to-noise ratio. And the solution roadmap is diversity, right? With diversity, you increase the slope of the error probability curve. So now in the second case, can diversity help? If you apply diversity, now, if you apply diversity, let's see, the error probability curve will be like this. In the noise limited region, since it behaves very similar to the flat fading case as if there were no interference, right? So the benefit of diversity will apply to this case as well. So the error probability curve will be steeper like this. So this is the benefit of diversity. Okay? However, as you get into the interference limited region, the irreducible error flow will still be there. Okay, so this is the curve with diversity. That is to say, diversity can only help on the noise limited region. It cannot help too much on the interference limited region. So it really depends on your operating region. As I said, if your target error probability is here, so that means you just need to operate the physical layer in the noise limited region. Then you can pretty much ignore the second star of irreducible error flow. You can just treat that as flat fading case and just apply diversity to improve the slope. Okay? But as I said, most of the time, if your target error probability is here, then you cannot ignore the second star, second trouble. In other words, you will be operating your physical layer in the interference limited region. So diversity in that case will not be able to help you. You need to think of some ways to deal with this irreducible error flow. Is that okay? And the issue is like the general solution is something called equalization. Well, conceptually, the root cause for this irreducible error flow is due to this interference, right? So if I have to improve or eliminate this irreducible error flow, I need to think of some way to eliminate this interference. Okay? Now there are different ways to do this. In a general way, it's called general method in this kind of category is called equalization. As we state in note, equalization. Now one way that we can do equalization is what we call, well, one way to do it is Now, since these are the previously transmitted symbols, right? Now, when you're in the fourth time slot, when you're in the fourth time slot, you should have already decoded C, B, and A, right? Suppose you make a correct detection about the symbol you transmit in the previous 3 time slots. So you know about B, C, A. You also know about the channel fading coefficient, alpha 1, alpha 2, alpha 3, alpha 4, from channel estimation, as we talk about, okay? Then in that case, at the fourth time slot, that means you can regenerate this term. If you can regenerate this interference term, you can subtract these terms from your observation, right? If you are able to do perfect cancellation, then that means what you would do is you would take this observation, subtract it with alpha 2 hat, C hat, plus alpha 3 hat, B hat, plus alpha 4 hat, A hat. These are the regenerated ISI. If you subtract this, then this, I call this R4. This R4 will contain just the good term and the noise only, right? And in this case, when you demodulate based on R4, your performance will be the same as the flat fading case, the blue curve, if you can do perfect cancellation, okay? Now, however, of course, you can never do perfect cancellation because now the channel estimate, you always have errors. You always cannot get the exact knowledge of this channel fading coefficients, okay? You may also make mistakes in the previous detection. Now, if you make mistakes in the previous detection, C hat is not equal to C, B hat is not equal to B, then you're thinking about subtracting an interference. But if you're subtracting with the wrong detector symbols, you are actually adding interference to the observation, right? So therefore, you can never do perfect cancellation. But I don't want to talk about the detailed mechanism of this equalization. But the thing is, now, despite you may not be able to do a perfect cancellation, as long as you can, after cancellation, you may still have some residual interference. As long as this residual interference power is substantially reduced, then this beta, this denominator in the beta, the saturated SINR, will be much smaller. And then in that case, this beta will be much higher. And that will help to push the error floor lower. You may still have error floor, but the error floor is lower. Practically, you just need to, you may not need to eliminate the error floor. You just need to push the error floor below your operating target, and that would be good enough. Is that okay? So that would be the kind of the equalization strategy. Now, there are different ways to estimate the ISI and cancel the ISI. Some will do something called zero forcing projection. Some will do this, what we call successive interference cancellation. And there are different ways to do it. So it's a whole portfolio of solution. But in general, what I want to say is, let me erase this. Unlike diversity, the complexity is pretty manageable. Equalization. If you are thinking about doing optimal equalization, the complexity is exponential in terms of the number of resolvable symbols. So that means if you are talking about 40 symbols instead of 4 symbols, 40 resolvable symbols instead of 4 resolvable symbols, the complexity is not just increased by 10 times. The complexity will be exponential in 4 to 40, okay? And you know, any algorithm that have this exponential scaling, that means this algorithm is not scalable. That means you can rely on this algorithm to handle some small number of resolvable symbol cases, but you cannot use the same solution to deal with a large number of resolvable symbols. Okay, the same solution cannot scale. And that is the challenge, okay? So unlike diversity, where you have systematic solution roadmap, here, when you hit this 2 stars of trouble, especially the error floor issue, you don't have a systematic solution, okay, because of the complexity issue. In general, okay, of course there exists some low complexity solution, but let me do it this way. So is this something we can ignore? Okay, so let's look at a table for the generation. So let's say this is a 2G GSM system. And then let's say this is a transmission bandwidth. This is the coherence bandwidth. And this is the number of resolvable symbols. So let's try to do a table of comparison. So for 2G, let's say GSM systems, do you know what's the transmission bandwidth? Megahertz or kilohertz? No idea? It's actually 200 kilohertz. Okay, it's a 2G system for voice, for mobile voice service. The transmission bandwidth for each user is 200 kilohertz. Now, GSM system is designed to provide outdoor coverage, right? So for outdoor coverage, what is the order of magnitude for the coherence bandwidth? Remember, coherence bandwidth is a parameter to characterize how severe is your multipath, right? So typically, the order of coherence bandwidth for outdoor is about 100 kilohertz, okay? Because for outdoor, the delay spread will be larger, right? So therefore, the coherence bandwidth will be smaller. So it's about 100 kilohertz. So if you do the math, that means for GSM system, the number of resolvable symbols, the channel memory, is around 2. So that means for GSM, you need to deal with this equalization problem. You will have irreducible error flow for GSM system already, okay? Now, what about 3G? For 3G system, which we will talk about in the next chapter, what's the transmission bandwidth like? What would be your guess, intelligent guess? Would the bandwidth be larger or smaller than this for 3G? It can only be larger, right? Because the data demand is always ever increasing. So in order to meet this ever increasing data demand, you can, of course, you need higher bandwidth for that, right? And for 3G, what we call later on wideband CDMA, the bandwidth is 5 megahertz. Now for 3G, about the operating environment, is there any difference? Not much difference, right? It's also designed target for outdoor propagation, right? Outdoor coverage. So the coherence bandwidth, which depends on the environment, operating environment, is more or less similar. Now if you do the math, in this case for 3G systems, the channel memory, we are talking about 50. Okay? Now continue the logic, 4G LTE system. Of course, you will guess the transmission bandwidth for 4G can only be larger, right? Because the data demand for 4G would be much higher than 3G. So, and the basic version of LTE has a bandwidth of 20 megahertz. Okay? Now, 20 megahertz 4G, obviously, the operating environment will be similar, outdoor propagation. So, coherence bandwidth is across generation will be similar because they are designed to operate at similar outdoor environment. Do the math, 200 resolvable symbols. So that means you send a letter A, you have 200 copies following. Or the beta are erased, you have 199 terms in the denominator. Okay? So 5G can only be larger and larger, right? So if you go through this trend, you will see that this two-star trouble is not something we can avoid. It's not something that this is just on the edge case, and most of the time we can get away by operating in the fat-fading case. This is not the case. In fact, it's growing across a generation. It's actually getting more and more severe. Okay, so it's something that we need to face it instead of we can bypass it. And as I said, the problem is we know, okay, solution roadmap is equalization, but brute force equalization, that is, if you dump all the burden of the equalization to the receiver, this brute force equalization has an exponential complexity, which is not scalable. So this brute force equalization at the receiver may work for GSM, and indeed GSM is using, there is an equalizer on every GSM mobile receiver. Okay? But GSM just need to deal with 2 resolvable symbols. But the same brute force equalization method in GSM cannot be used to deal with these cases, right? So, so brute force equalization, dumping all the effort to all the burden of equalization to the receiver will not work, will not be able to scale. But then how do we have a robust system for 3G and 4G? Not even talking about the data rate, but just maintaining a robust physical layer with a reasonable error probability. How do they get over this irreducible error flow? Or how do they get over this irreducible error flow with reasonable complexity equalization? That is itself a big challenge, right? So here is a typical solution roadmap. So dumping all the burden to the receiver is not a solution because of that constraint. So in order for you to have some opportunity of low complexity equalization, the transmitter will share an important duty. Transmitter can send some signal with some built-in structure. And the receiver, by exploiting this built-in structure, may have the possibility of having low complexity equalization. Okay, I repeat. The transmitter shares an important duty of sending out signal with some built-in structure. I will explain what we mean by built-in structure later on. And then the receiver receiving this signal with some built-in structure from the transmitter, it will be able to exploit this structure and have low complexity equalization possibility. So what are the examples of so-called built-in structure? One example is what we call spread spectrum. Have you heard about spread spectrum in undergraduate? Probably heard about the terms, right? So we'll talk about this in detail. Now, spread spectrum, basically, as we'll discuss later on, the transmitted signal is not just ordinary modulation symbols. The transmitted signal will be modulation symbol spread by some spreading sequence. Okay, so you can visualize that as the transmitter will chop a modulation symbol into many broken pieces. Okay, these are the built-in structure. And the receiver, by exploiting this so-called spread signal structure, the receiver has something called wake receiver. And the complexity of this wake receiver is only linear order of complexity. So this is much more scalable. And the fundamental reason why you have this low complexity receiver that can deal with this ISI problem is not because the receiver is clever. The fundamental reason that it works is because the transmitted signal have some built-in structure. And the wake receiver is just a clever way to exploit that structure. Okay, I will talk about the details, and by then you will know what I mean. Okay, so that's one example. And that's why 3G systems, the CDMA systems, is the fundamental technology. The spread spectrum technology is the fundamental technology behind different versions of the 3G standards. So all the 3G standards in the world are essentially based on spread spectrum technology, because that is one example that can give you the low complexity equalization across the frequency selective filtering channels. Okay. Another example, OFDM. You probably again heard about this term, OFDM, which is the fundamental technology behind 4G. Okay, and similarly, OFDM, the transmitted signal in OFDM are not just ordinary modulation symbols. They are basically having this built-in IFFT structure. It's a transformed signal from, so the modulation is done in the frequency domain, and then they transform back to the time domain to send out the waveform. So that is another built-in structure. And because of this built-in structure, the receiver of the OFDM system is using FFT. So you can think of FFT as an equalizer at the receiver. The reason, so FFT, the complexity is n log n. Now n log n is slightly worse than linear, but it's pretty much linear because log is growing very slowly. Okay, so this is almost linear. So the complexity scaling of these OFDM receiver are also very scalable. Okay, and that's why OFDM is the fundamental technology behind 4G LTE systems. Okay, so these are two examples why it works, why it enables such a wideband transmission over an outdoor propagation environment, and you can still overcome this irreducible error flaw. The reason is because the transmitter, the signal transmitted by the transmitter have various built-in structure, and that provide opportunities for the receiver to exploit the structure to achieve low complexity equalization. So in 5G, if you work in this area, there is one of the topic called waveform design. It's also a very popular research topic. By waveform design, again, is designing some built-in structure that can be exploited by receiver to overcome these kind of frequency selective filtering problems, the two-star trouble. Okay, so now of course what I say, you should not dump all the burden, all the equalization burden to the receiver. If you do it this way, the receiver will end up having exponential complexity of equalization, and that cannot scale. So typical solution, especially when you go down the generation, the transmitter plays a very important role. Transmitter should design some built-in structure in the signal that is transmitted. And then this provides opportunity for the receiver by exploiting this, whatever you call built-in structure. The receiver will have the opportunity of overcoming the ISI with reduced complexity. Okay, so that is the solution roadmap. But of course, it's not that straightforward as the diversity. Diversity is very simple, right? We just need to answer two questions: where can you create diversity observations, and how do you combine diversity observations? And things are very systematic. But when you get into equalization, the design space is what exactly is the structure you want to create, and how do you exploit this structure, so-called structure, to achieve low complexity equalization. These are you have a huge space of design available. So it's not that systematic anymore. It's more or less like a case-by-case design. So that's why this is more challenging than the first frequency flat fading situations. Is that okay? Okay. So later on, so I just state the principle. But later on, I will. So I don't think we have time to talk about OFDM. Well, okay, not here, but in the next semester there will be another course that we will talk about OFDM briefly as well. Okay, but we will focus mostly on the spread spectrum. Okay, and then with this, when we talk about spread spectrum, we will explain in detail what exactly are the structure and how the wake receiver exploit the structure to achieve so-called this low complexity equalization. Okay. Now, so far we talk about point-to-point communication. Well, we walk a long way from the beginning, right? So we talk about what is information, and then we talk about how to design transmitter and receiver to deliver information from one point to another point. And then we talk about, and as a toy example, we talk about one simple channel, additive white Gaussian noise channel. And then after we understand how to design the modulator and demodulator, then we talk about, again, point-to-point communication, but over a more practical channel, mobile feeding channel. Okay, and we talk about these two cases. First case have one star trouble, and then the solution roadmap. And the second case have two star trouble, and then the solution roadmap. Okay, so now it's high time for us to talk about extension to multi-user, because most of the practical systems are designed not for single user, but for multi-user. So how do we accommodate multi-users? Okay. Now to explain multi-user, we need to explain the concept of so-called multiple access. So the situation of multi-user is like if you consider, let's say, the uplink of a mobile system. So you have mobile station, a lot of mobile station talking to the base station. Okay. So the task of the base station receiver. So it's like I'm the base station receiver. You guys are the mobile transmitter. Imagine a scenario. Each one of you have some message you want to tell me, right? If there were no coordination, so you guys randomly transmit your information to me, and if my task has to simultaneously detect the data symbol transmitted by each one of you, okay, this is called multi-user communication, then my task will be super complicated, right? So in other words, if all these transmitter transmit the symbol without any coordination, then my received observation would be a superposition of all this multi-user transmission plus noise, okay? So if this is the case, my task is based on this observation. I have to guess what could have been transmitted by each one of these users. Then this is much more complicated compared to the point-to-point case, right? In the point-to-point case, remember how do we design the demodulator? The demodulator as a black box will give you a noisy observation which contains the transmitter symbol and the noise. The receiver has to guess what could have been transmitted behind this noisy observation, right, in a single user case. But now in a multi-user case, again, the input to the receiver is still the noisy observation. But now this noisy observation contains the transmission from multiple users simultaneously. And the receiver has to guess what could have been transmitted by each one of these users. So this is a much more complicated problem. Again, brute force solution requires exponential complexity. So it's, again, not something that can be scaled. So obviously, we need to have impose some kind of coordination among this multiple users transmission in order to relieve the burden of the base station receiver to receive the signal, to detect the signal from different users, right? So therefore, we need to have some kind of coordination among these users. So there are three typical popular ways to do. They are by no means the only method. There are many, many methods, but these are some commonly used methods with proven implementation that are effective in coordinating the transmission. so that the receiver can support multiple user communication. The first one is called FDMA, frequency division multiple access. Okay? In other words, we can try to partition the resource. Suppose I'm an operator. I got a license with certain bandwidth. And then I partition my bandwidth into many frequency slots. And then I start assigning each one of you to transmit on a different frequency channel. In this case, you can transmit simultaneously, but on different frequency channel, right? Then I can pick up different transmission from each one of you. I'm just a radio. If I want to listen to your transmission, I just need to tune to your frequency and will be able to detect your signal, right? So that is called frequency division multiple access. In terms of the picture, it's like this. So this is the bandwidth of the license you have. So instead of transmitting over the entire bandwidth, we first partition the bandwidth into many tiny frequency slots. And then we start assigning different users to transmit on different frequency slots. So the user owning a particular frequency channel can transmit at any time, at all time. Okay? So if somebody walk into this classroom, you guys are transmitter and the receiver. If somebody randomly sample this classroom, that guy will see all of you transmitting simultaneously, but at different frequency channel. Okay? That's one way of partitioning the resource. A second way of partitioning the resource is called TDMA, time division multiple access. So this is the other way. We try to partition the resource, the time dimension, into different time slots. Okay? So, and then we assign different users to transmit at different time slot. At any time, there will be only one guy transmitting. But that transmitting guy will be able to use the entire bandwidth of the spectrum. Is that okay? So if somebody randomly walk into this classroom, he will only see one guy talking at any time. But that guy cannot keep on talking forever. That guy can only transmit on the assigned time slot. When the assigned time slot expires, that guy has to shut up and let the other pick up the channel. Okay? So it's like this. Okay? In this time dimension, you partition into many time slots, and then you assign one time slot to one user. So that user can only transmit on the assigned time slot and remain silent for the other time slot, and let other transmit. Is that okay? So that's why at any time you only see one guy transmitting, but that guy transmitting will be able to transmit over the entire spectrum. Okay? So FDMA and TDMA are just two complementary ways of partitioning the resource. Okay? One is partitioning the resource over frequency dimension. The other is partitioning the resource over time dimension. All right? Now, the other way called CDMA, code division multiple access. The best analogy I can think of is in code division multiple access, you don't partition the resource on the frequency or time axis. So each user, like each one of you guys, will start talking to me simultaneously, but using different languages. Okay? Suppose you're talking to me using English, you are talking to me using Chinese, Mandarin, and some of you are talking to me using Cantonese. And suppose I know all this language. You can still imagine, although your voices overlap with each other over time and frequency, the fact that you are speaking with different language, I can still selectively pick up some of your messages, right? So that would be the analogy for code division multiple access. So you can see that with code division multiple access, the transmission from different users, they are not separated by time nor frequency. They overlap in time and frequency, but they are separated by something called code domain. Now, we will talk about this in detail later on, okay? Well, in fact, I don't think I have time to go into the details. Okay, so this is just the three common ways of multiple access. So that the objective or the motivation of this multiple access scheme is to impose some coordination among users' transmission so that the receiver will have an easier job to decode what could have been transmitted by each one of you, okay? So I will stop at this point, and then I'll continue to talk about these three ways next time.